Hello, my name is Isabel Rangos. This is Lab 1, exploring the interaction between charged tapes. By creating two charged tapes, one secured on each end and one being moved by my hands, I was able to observe their interactions. I then measured the distance at which they began to interact and repel from each other, and used this value to calculate the charge necessary on each tape to make one tape float above the other. Following these calculations, I created a computational model representing the tapes as a single point charges, showing the gravitational and electrical forces acting on the top tape. The fundamental physical principles involved in this experiment are the gravitational force and the electric force. I began the experiment by measuring out two equal lengths of tape. I then used these lengths to calculate the mass of the tapes. Then, when I conducted my experiment, I observed and recorded the distance at which the tapes began to repel each other, and the top tape started to float. I used these data, as well as the fundamental physical principles, to calculate the magnitude of the gravitational force, which is equal to the magnitude of the electric force. I then used this calculation to find the charge of the tape necessary to make the top tape float. Using these calculations as my foundation, I created a computational model calculating the charge of the top tape, the electric field, and the electric force on tape B by tape A. This model also illustrates the tapes as single point charges, with arrows modeling the electric and gravitational forces acting on the top tape. Here is my computational model, with the image above illustrating the interactions between the charged tapes and the results of my calculations below. I found the magnitude of the charge on one piece of tape to be equal to 7.96894 times 10 to the negative 9 coulombs. In order to make these calculations and the computational model, I had to treat the tape as if it was a point charge, with all of the charge concentrated at the center. I also had to assume that each U-tape had the same amount of charge, evenly distributed along the length of the tape. I did not take into account air resistance, because at the point when I measured the tape, it was floating and not moving. Therefore, air resistance would have no effect on the object. What if electrons had positive charges and protons had negative charges? There would be no change in this experiment. The observations would be the exact same as witnessed in the initial experiment. This is because opposite charges would still attract and like charges would still repel. The electric interactions remain the same because the fundamental physical interaction is not altered by the changing of the charges assigned to electrons versus protons. We need to avoid handling the tapes as much as possible because we need to avoid grounding. Coming into contact with hands and other objects can give or take electrons away from the charged tape. If this happens, it changes the overall charge of the tape, making it unequal to the one that has been handled less. As well, if enough electrons are transferred, the tape will not be charged. Therefore, there are no electric forces acting between the two tapes, as the electrical interaction between them is gone. In conclusion, we were able to find that with a significant enough charge, the tapes will repel each other enough to make the secured tape float. At the highest point, when the top tape is not moving anymore and is floating, the gravitational force equals the electric force. This distance and the mass of the tape allows the calculation of the charge of the tapes, which is found to be 7.96894 times 10 to the negative 9 coulombs. This system can be modeled by point charges in a computational model illustrating the electrical interactions between the tapes.